going to finish this day nicely with a talk of degradation of amino acids by cosmic radiation by Professor Enio. Enio was an undergrad and a master's student at PUC here in Rio, and he did his PhD in Université Paris Sud, was a postdoc at Texas A&M in the US, and back to Rio, where he's a professor at PUC. So please, Enio, marvel us, and we'll ask you later.
Thank you for the introduction. Thank you for the organizer for inviting me. I guess that I'm going to change completely the direction of the talks. Starting to talk a little bit about degradation of organic molecules by radiation. The outline of the talk to be a little bit about this. Why glycine, why valine? How they are formed in space. They exist there, so how they have been formed. Some reasons to produce and to destruct those molecules are radioactive decay, cosmic rays, and why in comets and why in asteroids, for instance. So this will be a kind of a general discussion. A very large introduction, probably will be half of the talk will be there. And then I'm going to show you some experimental results that we have performed here in Rio about these two amino acids. And finally, 5 minutes of discussion. For those that do not know what the glycine is the simplest amino acid. The mass is 75 mass units. The amino acids are very, very important as bases of proteins. This particular amino acid is not the chiral molecule. The others, probably most of the others are, but this is not. In the solid phase, which is supposed to be the phase that exists on comets, is solid, and there are 3 possibilities for crystallization. For us, amino acid is part of this structure, and this structure we have in many, many parts of our organism. It's really very important. It's made of, is a helix, made of 3 amino acids, so glycine is one of those 3. It's quite very important. The general structure of the amino acids is 4 parts. You have this COOH, this is a carboxylic acid group. And then the other side of this carbon, which is called the alpha carbon, there's a nitrogen and 2 hydrogens. A hydrogen is there, always, except in the iso amino acid. And here, there's a radical, which turns out to be, for the glycine, the hydrogen. That's why it's the simplest, because you have just a hydrogen here. The glycine has been discovered in the solar system. My research is not very extensive, so I saw that in these meteorites, this stardust in 2004, and very recently, Rosetta made a very, very nice work analyzing the glycine in the gas phase. I'm going to discuss a little bit on that. And in the interstellar medium, there is still some debate. There are people that think that it's not the glycine, others say that it's glycine, so I just put the glycine like here. And those are seen by a radio telescope. Well, I guess that all of you know about the Rosetta mission. The Rosetta orbit this P67 Churyumov comet about 2 years. And orbiting these 2 years, there are lots of experiments, but in particular, Rosetta has this very, very nice mass spectrometer. This spectrometer, which should be about 1 meter long, is a reflectron type time of flight. Time of flight means that the mass of the ion is measured by the time that the ion goes from here to there. And on top of that, there is a mirror, and it's an ion mirror, so the ion goes there and comes back. And with this, the mass resolution is fantastic. It's about 3,000, which means that this instrument is able to differentiate the mass 3,000 from 3001. If you can imagine that this is in orbit with a very low consumption, it's a nice machine. An example is here. This is one spectrum, mass spectrum, took by this instrument, where you can see 74, 75, 75.05. So two different molecular species, both with the mass 75, can be resolved. So that's why we know that the glycine is here and not other elements. Let me tell you in another way. This machine is able to recognize a proton from a neutron. So one species has 40 protons and 35 neutrons. The other one has 41 protons and 35 neutrons. So both giving the mass 75, but it has been resolved. So it's very, very interesting. And so take the area of this peak every 20 seconds, and for many, many months, this spectrometer called Rosina was able to see how the density of a glycine changes with the distance to the comet. And this is shown here. So in kilometers, divided by r square, so it is possible to see that the density of the glycine is constant, which means that it goes down 1 over r square. So this is a gas phase analysis, took for a month. It's a very, very nice, so there is no doubt about the glycine. This is the second amino acid. In this case, you still have the 3 groups, but now the group, the radical, is a little bit more complex. So you have a carbon, a hydrogen, and then 2 CH3 groups. You can see better here. So the hydrogen was here in the glycine, and now is this radical, but it's the same structure. Because of this group, the mass is much higher. Again, it's precursor of proteins. It's absolutely necessary for us in our body, but we do not produce valine. So we needed to take valine in our put. It's very important for the neurological system. And differently from the glycine, it's a chiral molecule, which means that there are two types of molecules, which is the mirror reflection. If you look carefully, you can see that this hydrogen, which is here, rotates 180 degrees, and this part here is rotated again. So this is the mirror image. And this valine is called L-valine, and this is D-valine. And it turns out, it's not very clear still, we only, it's necessary for us only the L-valine. The D-valine is not used, is not formed by the enzymes. However, the D-valine appears in space, which means that the origin of the valine in space is not biological. It's one of the way that people used to do analyze contamination. Contamination for humans is different from space. So valine has been found in several meteorites. It has been produced in the famous Miller-Urey experiment. So it's one of those amino acids formed by the discharge in gas. I guess that's all. This is chromatography, so it's something different from mass spectrometry, but what they do is to take extract for a series of meteorites, and then they analyze by the rotation time what could be the amino acid, and those are the amino acids found in meteorites. So amino acids is something very special and sure that exists in those material. These two that we are discussing are this one and this one and this one. So you can see the D and L here, the D and L here, and you can see also that the number 6, which is a glycine, is in most of the cases one of the biggest peaks. So there's lots of glycine in the meteorites. Okay, so questions. How they have been formed there? What's the process? And the second question, once they have been formed, how they can survive there for millions of years, knowing that ultraviolet, solar wind, galactic coronal ray, and gamma, alpha, and beta from natural decay is the radiation that exists in space. So we needed to answer that. And for models, what should be the mean lives of those amino acids, which means for each radiation, how long the molecule survived. 1 second, 1 year, 1 million years. So this is the kind of question that we need to know to answer. Let me start with the radioactive decay. It's not very common to talk about this, but it's quite important. So let's assume that you have a grain in space. It could be an asteroid as well. And usually, you know that the comets has a very low density, half of the density of the water, which means that they are very porous, which means that there are gas, there are liquids or solid, depending on temperature, that are inside the rock. So you have probably water or ice or CH4 inside as well. From the formation of those grain, and these are the where the colleagues are explaining to you how the planets and stars and grains are formed in space. These radioactive nuclei, they are distributed inside the grain, inside the meteorite or the asteroid, which means that the ice or organic molecule, they are in contact with the radiation inside, not outside. Outside you have the solar wind that comes from the sun, or you have the galactic rays comes from everywhere, but those penetrate not more than millimeter. In fact, they are stopped in microns of the surface. But in the interior, you have the natural radioactivity everywhere, everywhere. So this is a interesting way to see if molecules can be synthesized by this method or destroyed by that. So let me talk a little bit about this process. We have 4 natural chain. These 4, the first one is Neptune, has 2.2 unities million of years. So because of we are 4 billion of years from the production of those material, this chain is now complete dead. So we have probably just the stable products. But those 3 are active. 4 billion years, 0.7 billion years, 40 million. This is the age of the universe. So if this thorium was produced during the Big Bang, which was not this younger, but you can still see the decay of this thorium. And when the thorium decay, then you have a cascade of decay, and each cascade you have alpha radiation, beta radiation, and lots of gamma radiation. So whatever this thorium is inside an asteroid, you are going to have all the products and all the radiation come from them. So again, once this alpha is launched, you have a cascade of many others. So it's a lot of radiation, lots of radiation. Not by another reason, this and these chains are used in nuclear plants. So they are there. Another way to see the same effect, and here is in billions of years the age of our solar system. If you imagine that the formation occurred here, 4.5, these 3 series decay like this, so we still have about 80% of the initial quantity, number of nuclei of this thorium. We have about half of uranium 238, and which is that's used in nuclear plants. And we still have this chain which gives another series almost destroyed. But if you look what happens in the first billion years, or first half billion years, the quantity of decays, which means radioactivity, was enormous, much more than we have today. So this radiation has to be taken into account for the studies of
The red line shouldn't be the Uranus, not thorium.
Yeah, this should be U35.
Okay.
Yeah. Okay. Knowing that it's possible to estimate the dose that this radioactive material can be delivered to the comets. So there are people that did this, and the answer is about 14 mega gray. For those that are not familiar with the gray, 1 gray means 1 joule per kilogram of energy. 1 joule of energy per kilogram. If you, I don't hope that you need, but if someone needed to be treated in cancer, we are discussing milligray, milli. Here we are talking about mega gray. So there's a lot of radiation that has been delivered to this ice or molecules in comets. Okay. Let me now say some words about solar wind and about the galactic cosmic rays. They are the same ions. So there are hydrogen, helium, deuterons, carbon, oxygen, nitrogen, iron. Solar wind and the galactic cosmic rays. But the energy distribution are very different. Solar winds, we are talking about keV. Galactic cosmic rays, we are talking about GeV. So the consequences are different. The penetration depth, very different. The galactic penetrates in clouds, penetrate on asteroids much more than the solar wind. The destruction rate of the molecules, because this depends on the stopping power, which means the energy that each of these radiation deliver per unit length. And this is also very different. And the relevance of the projectiles is still very different. For instance, solar wind, hydrogen is very important. For galactic cosmic rays, for this kind of thing, it's not. It's iron is the most important. So let's go a little bit more in detail. This is a kind of picture of our solar system. Probably you have seen this or similar to that. So the sun is here, Alpha Centauri is here. This is in log scale. And what you should see here, a division. There's a wall here. And this wall is made of hydrogen. So this region here is the habitat of the solar wind. And this region here is the habitat of the cosmic rays. So different. Here we are talking about the keV per particle. Here we are talking about MeV, hundreds of MeV per particle, per projectile. So very different. There are some names that you should know. This is the way that we get information about what is going on here. So these 2 voyages are here now, just after this heliopause. So they are getting information about the cosmic rays without being disturbed by the solar wind. So it's something that is going on today is different. They are here since 1 year or so. What else can we? Well, so you may ask, why this hydrogen wall is there? And the reason is easy. Solar wind comes from the sun with this velocity. And this velocity is practically constant over here, but at this point it started to be blocked by the stellar wind or by the fact that the solar system is just coming down and to the apex. And this is a kind of shock wave. This will occur with the comets, and this will occur with the Earth as well. Why this is important? Because the density is different in these two regions, the gas density. Okay? What I was saying is, well, hydrogen is everywhere. This morning we knew that we have 1 proton per cubic centimeter somewhere. And this region of the space is much more than that. It's much more than that, because the pressure is 10 minus 14, 10 minus 12 torr. But where is the point? You have a hydrogen comes from the sun, and when the hydrogen gets close to the Earth, you have this kind of this perturbation. What's the origin of this? Collision. Collision between molecules. So the collision will produce this this kind of flow, and well, there's the magnetic field as well. And the point here is from here to here, you have 10 to the power 28 difference in the density of the particles, or pressure, if you prefer. So, what is the mean free path of a particle here? This calculation, very with the hands, you may consider that it is 1 over the density over the cross-section. If you take 1 angstrom for the atom, so square is 10 minus 20, so is the Bohr cross-section. This is the density, comes from this pressure, and this gives you what is a typical free mean path in space. Is about the distance from the Earth to the Moon. So this means that the 1 particle can go to the Moon without any collision, in average. And those distance here, which is more than the distance from the Earth to the Moon, means that you have many collisions there. So why it is important? Because these collisions will produce a hydrogen shock wave in front of the comets. If your comet goes that way, the hydrogen is here, and then you have the coma over there, and you have these 2 light comas, one which is produced by the sun, which is due to the destruction of water, and then the other one, which is yellow, is produced by just the dust that stays along the trajectory. So this is a little bit a structure of a comet. You have the ice in here, which sometimes does not exist anymore, which is the case of this P67. There's practically no water from outside, the water comes from inside. So these jets that I'm showing here is coming from the interior. So the glycine is not on the surface. The glycine is coming from meters down the surface. If you look to here and if you look to there, you can see the same process. This again is collision in the space. If you go in this site, you can see a video of this. This is a animation. Animation of what? Solar wind, and then the comet 67. And what may result from this video, from this animation, is you can see that the solar wind does not touch the surface of the comet. So asteroids and comets, you have a difference there. The comets, you have a gas, you have jets. And these jets will block the solar wind. While in the asteroids, you do not have that. So you may think that the chemical processing on the surface of the asteroid of grains is different from the comets. So this comes just simply from this view. So again, this means mean-free path. So when I see this kind of flow, I say, well, in the space I have gas, low pressure, and with the velocities, which is this one here, 400 kilometers per hour. The collisions are producing this kind of flow. So what's the point? There's no interaction between 4 keV particles from the sun with the surface of the comet. How is the energy distribution of the solar wind? You have here the energy. The energy is in the MeV per nucleon. And this 400 kilometers per second is 1 keV, which means this region here. So you have, I do not have the protons here, but the protons are there. So this is telling me that most of the particles that are interacting with ices coming from the sun, they have this energy, keV. Well, there's a list of flux comparing with UV and comparing with cosmic rays. You can see that the flux is very different. The energies are different and the flux are different. Why those? Because those are the ionized radiation. That's what you need to see what they do. If you compare these numbers with an accelerator, which is our case, we may have a 1 microampere of proton beam in the accelerator. This is the surface of the target. Mean this kind of calculation, the result is 1 hour of exposing your sample in the accelerator corresponds to 200 years in space. If this current is reduced by a factor 1,000, which means 1 microampere, this means 200,000 years. So you can see how a target changes in space just by radiating in a computer. The same idea, but now for galactic rays. For galactic rays, the scale here is GeV. So the maximum of protons and helium occur in GeV energies. It's just for you to have an idea what we are talking about. The last thing that I need to tell you about those is the penetration. Again, you have here the energy of the particles, hydrogen, helium, carbon, iron, and the penetration depth in millimeters. So depending on the energy, they will penetrate a lot. So 1 GeV hydrogen can penetrate 1 meter in the ice, while an iron will penetrate 1 millimeter. What this is telling me, that the iron will stop very quickly, so all the defects, all the chemistry produced by the iron will be delivered in the first millimeter, while in the hydrogen is deeper. If you think that this is a comet, and for the comets, this kind of energy is so high that the penetrating jet, so the point again is the solar wind is not processed in the surface of the comet, but the galactic comet ray are. And are a different way. The hydrogen goes deeper than the iron. Okay. I'm going to change gears. Conclusion up to now. I gave you some arguments to say that the solar wind does not process a surface of an active comet. Active means close to the sun. If you go with the comet far away from the sun, the flux decays with the square of the distance. So the comet is not active anymore, but the flux is much smaller. So in both cases, the interaction between comets and solar winds are not very high. Nevertheless, the glycine is there. So how the glycine has been formed if you have this problem? Possibilities. The galactic comet rays are much more energetic, and they can penetrate the exosphere of the comet, which the solar wind does not. Another possibility is UV. UV can penetrate, can touch the surface of the comet, even active. And the third point is the decay, uranium decay, which I mentioned before. So you have 4 processes, and perhaps these 3 are more important for comets, and this could be important for asteroids. You may argue that asteroids, they do not have too much ice on the surface near to the Earth. Those which are far away, they have lots of ice. Okay, so now I'm going to this second part, which are the experimental results. This is the accelerator that we have in PUC at this in Rio. We have an ion source where we can produce hydrogen and helium, for instance, which is accelerated up to few MeV, and then analyze again. It goes directed to a chamber, and in this chamber there is a cryostat, so you can have the low temperature targets, and you can analyze by infrared in the same region that has been used for astrophysics. Just for you to show how it looks like, here's the beam coming into the experimental area. Here is inside that experimental area, which is controlling humidity, temperature, so on and so forth. The chamber is in here. This places the chamber for room temperature targets, and the infrared spectrometer is here. So it's dedicated to this chamber. Some results. The first result is glycine with protons. You have 2 types of glycine, an alpha and beta glycine. They have a different crystallization. This is for non-irradiated samples, and this is the infrared spectrum. The first observation, the infrared tells very easily which is the structure. So the alpha is the red one, and the blue is the bad one. So no problem for characterization. The second step is let's irradiate them. So you can see the evolution as a function of the fluence for the beta glycine and for the alpha glycine. So here is just to look like very similar, but the point is we can follow the degradation of both the species, and the result is plotted that way. So here is the radiation time, which is transformed in fluence, and what we saw is from the beta glycine, the evolution is different from the alpha glycine. The alpha glycine is destroyed 5 times faster. So it's the same molecule, just the fact that they are crystallized in different ways. This fact results that it's easier to break one molecule in that structure. Okay? It's the same molecule, it's just the way that the environment is made, make this. And we have analyzed for different bands. So this one is for this band here is the amino group, and this is the same thing but from the carboxylic group. And well, again and again and again, it's always the same result. The beta structure is less sensitive to the radiation than the alpha. I told you that we need results. Result means cross-sections. The destruction cross-section of a glycine is 2.5 10 minus 14 square centimeters. And this has been translated into astrophysical units, say that this kind of glycine will live in average 1 million years in space. So 1 million years will destroy half of the population of that glycine. If you have the beta glycine, then it's 4 million years. So this is the result that comes from the experiment, and this is telling us that probably this one will has a higher probability to arrive here on Earth. Valine. The valine, we have used the different energies and the different ion beams and the different temperature as well. So that's a work that is going on in this moment. If you remember, valine has a curio, so D-valine and L-valine. Here is the spectrum of both. And the conclusion is they are identical. You cannot differentiate the two types the same way that we could from the glycine. The valine is identical. What happens if we change the temperature? So 10 Kelvin, 70 Kelvin room temperature. What we see is they're different. So lower temperature, the peaks are, the resolution is better, which means that the bands are not vibrating too much. Probably if the valine is in space, the temperature will be somewhere near here. What happens if valine receives different ions? So you have the hydrogen here, you have the helium, you have the nitrogen, and the nitrogen 2 plus. The conclusion is it depends on the energy of the projectile. So there are some that the destruction is very fast, and depends on the ion. You can put all these results in a table. Okay, I forgot. After certain times, the valine is destructed, but appears CO2, CO, and some new peaks. So these are products of the valine, which means that the valine has been, have degradation of valine, and these are the products. So it's possible to measure the cross-section of formation of this product, in this case for CO2 with the helium. So you can see that's proportional to the radiation time. Before going on, I needed to tell you about stopping power. So what the stopping power is a friction force, microscopic friction force. When an ion penetrates into the matter, it stops after a certain distance. What makes the ion stop? The friction. So the friction is the number that we put here. What this is telling me, if I have a hydrogen, helium, or nitrogen, if I increase their energy, the friction increases. But if I increase too much the energy, the friction decreases. This means that the radiation goes through the object. That's why you can go to a very high energy particle and have no problem at all. This means that the radiation is going through you. The maximum of the friction is the worst thing. If you do cancer treatment, you need to put the patient in here, where the radiation will destroy the cancer. Not in here, not in there. So, why this is important? Because friction means that you are transferring energy to the sample. Higher is the friction, higher is the temperature of the sample, because higher is the transfer. The results are analyzed in function of the friction. And this is the destruction, which means the cross-section. For a hydrogen beam, for a helium beam, for a nitrogen beam, there's fluctuation here, but don't look into that. And you can see that higher is the mass of the projectile, higher is the destruction. This is in log scale, which means that the hydrogen, there's a lot in space, but the destruction rate is small, while the nitrogen is much less, but the destruction is much higher. And if you take iron, which is still less than nitrogen, but the destruction is very, very high. So they mean that you need to look into all of them. Let's talk a little bit about the physics. If you have a grain in space, and if you have a proton comes from the sun, and if the proton goes through the grain, there are many things that are important, but we are looking to only three. There's a kind of a splash here when the projectile touches the grain, and this splash is called sputtering. The sputtering can be neutrons or ions, which means that this species can go out ionized or not. once the projectile traverses the grains, you have sputtering from the other side. So you have two sputterings, entrance and exit. Inside the grain, there are dissociation, molecular dissociation. Once the molecule dissociate, you have chemical reactions. So inside the grain, the radiation is inducing chemical reactions. And there's some heat inside the material. And if there's heat, the crystal change the structure, which means crystallization, compaction, so the structural modification. So these three phenomena are important, are happening, let's say, always, and then you need to look on them. We did, and this is the case of Valin. So again, here is the radiation time. Here is the quantity that resists and the target. In the beginning, you have a kind of very quick destruction, and in fact it's not a destruction, but it's just a compaction. So the material under irradiation is string. Then you have a long part. This is a log scale, so this is exponential decay. And here you have chemical destruction, chemical reactions, so association. And finally, when the target is very thin, you have a sputter here, a sputter there. They become too close, and probably the target explodes. So you finish with this kind of collapse, and then here the target is completely destroyed. So three process: compaction, which is crystallization; dissociation, which is chemistry; sputtering, which is a physical chemical effect. What else can we say about Valin? After a certain time of radiation, the Valin is destroyed, but in the target you have this kind of new material, and we think that is what the people call toluenes. So toluenes is a very complex polymer that is the result of irradiation of organic material. After a certain time, the color change. I don't know why. This is part of the work that is going on at the university. Let's go to some conclusion for this point. Okay, we have tried different ways to prepare the sample, and the position by vacuum is the best one. The cross sections of the structure of Valin are those numbers. So these numbers you need to compare with the numbers with UV or with KV cosmic ray. So reading this, you know how fast the material has been destroyed. We have observed that after a certain time, these are the products of the Valin. And probably the CO is the destruction of the CO2, because the CO2 appears first and then we see the CO. The cross-section of Valin goes with the power 3.5 with respect to this friction force. So this is interesting because now you can predict what happens for other beams. Compaction is observed, except if you do kind of annealing of the target before. And this is a very, very important point for this conference. We do not observe synthesis. Why this is important? Because the idea of panspermia is you have the organic material, water, CH4, NH3, and with the radiation, you transform this into amino acid, which is okay, probably that way that this exists in the comets. But once the amino acids are produced, the radiation destroys it. So you cannot go further. So this is what we are saying. This is what we observe. If you bombard the valine up to the end, there is no synthesis anymore. The simple molecules go to a complex molecule. A complex molecule comes back to a simple molecule. We are not going to proteins. You may say, wow, just wait 1 million years and then you have proteins at the end. No. The most complicated thing that we saw is the toluenes. But the toluenes is a polymer, very complex. I don't think that you can produce life from the toluenes. But this is a very important point. I will finish with another example. Okay. For people that like to do models, we observe 3 phenomena: sputtering, chemical, and compaction. And if you see how they go on friction, one goes with a square, the other one goes with, this is wrong, 3.5, and this goes with the square as well. Because heavy ions have a higher friction force, a higher stopping power than light ions, the conclusion is heavy ions are much more efficient than protons. That's why I told you in the beginning that in the interstellar medium, iron is more important than protons. Not because there are more ions, the flux of ions is higher, but because the stopping power goes with the square. And this is a lot. Another thing that is important is how cross-sections, which means the destruction, goes with the target mass. This has been done for an ice because we do not have it for baleen. But the point here is the following. If the mass is increasing, which means that more complex is your target, formation cross-section is going down, destruction cross-section is higher. So look into this, you can see that more complex is the molecule, bigger is the destruction compared with the formation. This means that you cannot go further. So, and this depends on temperature. Room temperature, or in this case it cannot be room, but it means that it's easier to produce, to form a new species at a high temperature than low temperature. So there are 2 ways of treating this data, which is summarized here. If you have a low temperature cross-section, formation cross-section goes down, destruction cross-section not too much, and duration goes down. If you have a high temperature means 80 Kelvin, the formation cross-section goes down, but the destruction cross-section increases. Wow. So it's easier to destruct, which means that if you do the ratio, it goes down as well. So no way to keep it going. Conclusions. If you expect to form amino acid with radiation, go into high temperature. Because it's going down with the mass, do not expect to produce a protein. Okay, so These are the people that has been involved in this work. Cassia, chemistry, which is here. Christian's from the equator. Cynthia, which is here as well, doing the violin. And Eduardo is astronomers. Sergio Pirin, Vinicius, which is here. They are astronomers, work in the glycine. And Luis Mendes, physicist from Bahia, work in the glycine as well. So thank you very much.